Welcome back to the deep dive. This is where we take all that, dense information, the research papers, the technical blogs, developer notes, all of it, and we really try to boil it down to the core insights you need to keep up. And today, we're moving beyond the kind of basic large language models, the ones just generating stories or, chat replies. We're diving into the next big step, the specialized AI agent, the kind that uses tools, operates in the real world. It's the difference between, say, a clever parrot and a truly functional, reliable digital assistant. Yeah, our mission today is really to unpack the technical strategies that are making this happen. How are LLMs turning from just text predictors into, well, workhorses for complex tasks? We've been digging into the architectures that focus on stability, efficiency, and crucially, precision. We've identified three key pillars from the latest work in agent design that we really need to explore. First up, tool calling. This is foundational how we give LLMs access to live real-time data. Then second, we'll get into agentic research. This is fascinating stuff about automating the deep, structured way humans actually conduct research. And finally, we're tackling agentic RAG, using multiple agents to fix that big problem of getting fuzzy or irrelevant results when querying huge knowledge bases.
Absolutely. And these are just, critical topics because, the second an LLM needs info that wasn't baked into its last training run, think current stock prices, API updates, specific customer data, it just hits a wall, historically speaking. Tool calling is really the fundamental technique to fix that. It connects the LLM to live data sources, APIs, databases, whatever. It makes the model aware of the world as it is right now.
Right. But it's not just about plugging it in, is it? The sources we looked at really highlight a kind of core problem with the way this connection is usually built. It seems to center around reliability, how things fail.
Exactly. That's the traditional implementation we need to talk about first. You typically see this direct and frankly brittle link between the client application, the user interface, maybe a chatbot window, and the LLM itself, and the technical load on that client application. It's huge. That's really the root of the unreliability problem.
Hold on, if the LLM is just suggesting the tool, why is the client logic immense? Couldn't it just be like a simple wrapper that calls the suggested API?
If only it were that simple. The client has to do a lot of heavy lifting, both before and after the LLM gets involved. It needs to create and manage these really detailed tool definitions. Think of them as instruction manuals for the LLM. These definitions have to include the exact tool name, a very clear description telling the LLM when and how to use it, and all the input parameters perfectly structured so the LLM understands. And then you get into this multi-step loop that's just prone to issues. The client bundles the user's query with all those tool definitions, sends it off to the LLM. The LLM suggests a tool, maybe something like get weather, City, London. But here's the critical part, the failure point. The client application has to take that text suggestion, figure out what it means, actually execute the API call and network requests, and all that, get the result back, which might be messy, and then send that result back to the LLM so it can finally generate an answer.
Wow, okay, so the client isn't just passing messages. It's the interpreter, the execution engine, the error handler, all rolled into one. That sounds incredibly complex and honestly a bit fragile.
Yeah. It is absolutely fragile. And the sources point to two major downsides of this tight coupling. First, the risk of hallucinations goes way up. Because the LLM is involved in both suggesting the tool and potentially interpreting the result, things can get confused. The LLM might even invent a tool call that doesn't exist or misinterpret the data that comes back.
Which leads directly to the second problem, right?
Yeah.
The sheer engineering effort needed just to keep it from falling over.
Precisely. That's the second big disadvantage. The client logic has to be incredibly robust. It needs to anticipate and handle all the ways the LLM's suggested tool call might be wrong. Maybe the LLM hallucinates parameters the API doesn't accept or uses the wrong format. The client code has to catch that, maybe try to fix it, log the error, maybe restart the whole conversation. It adds a ton of complexity and points of failure right in the client app.
Okay, so the old way is brittle, error-prone, puts too much burden on the client. The logical next step, then, must be about abstracting that mess away. Which brings us to the strategic fix, embedded tool calling.
Yes, this is the key architectural shift. You introduce a dedicated library or framework. Think of it as middleware, a protective layer sitting between the client and the LLM. What this library does is pretty smart. It takes over responsibility for both the tool definition and the entire tool execution logic.
Right, so the big idea for developers isn't just that it's easier, but that by moving where the tool actually runs, you shift where failures happen. You isolate the risk.
That's exactly it. You decouple the running of the tool completely from the client application. The client's job becomes much, much simpler. The client just sends the raw user query, nothing else, to this library. The library handles adding the tool definitions, sends it all to the LLM. The LLM sends its tool recommendation back, but it goes to the library, not the client. And then the library executes the call itself. It gets the result, processes it, maybe cleans it up, and then sends the final formulated answer back to the client. The client is totally out of the loop during that critical, potentially failure-prone execution step.
That separation sounds like the core of improving stability. What are the concrete technical wins here? How does this make things more robust?
Well, the stability improvement is huge because the library, which is just predictable software code, is handling the execution. The chance of the LLM hallucinating about the results or the steps involved drops significantly. You've cleanly separated the unpredictable part, the language generation, from the predictable, secure part, the code execution.
And crucially, the library handed over the errors. That retry logic you mentioned sounds like a massive win.
Oh, absolutely. The library owns the entire execution lifecycle. That means it must include robust error handling logic. For instance, if an external API call times out or throws an error.
Like a 503 server error or something?
Exactly. The library can automatically retry the request, maybe with exponential backoff. All that complex logic for handling transient network failures. It's built into the library, completely removed from the client application's code. The client just asks a question and waits for an answer.
And this library approach, acting as a sort of universal translator and executor, it makes the system more flexible too, right? We're not limited to just calling external web APIs.
That's a great point. The library can encapsulate and manage all sorts of different tool types seamlessly. Yes, external APIs for weather or stocks, but also complex internal database queries. Imagine the LLM suggests some SQL. The library can safely handle the database connection, execute the query, and return the results. It can even manage local code execution, perhaps spinning up a secure code interpreter environment to perform calculations or data analysis tasks requested by the LLM. So embedded tool calling is really the blueprint for building reliable AI agents. Agents that can safely interact with the real world, make decisions based on live data, and not just be these fragile language things.
Okay, that really clarifies how we build a stable foundation for these agents to interact dynamically. Now, let's build on that. How do we scale this up to tackle really complex, knowledge-intensive work? That brings us to Agentic Research. This is where we move beyond simple single-turn interactions to automating those deep, iterative processes that, knowledge workers spend so much time on.
Yeah, the potential impact here is, well, it's huge. Think about sectors like legal, pharma research, complex finance. Agentic Research, using these specialized AI agents, aims to automate the really time-consuming, repetitive parts of research.
You mean the stuff where professionals spend hours, maybe even days,
Yeah.
just wading through documents, trying to synthesize information, often conflicting information, just to get a handle on a complex topic?
Exactly that. AI agents can potentially condense that kind of foundational work, the deep digging, the recherche, as they say,
Right.
into minutes.
There was a really striking example of this in the sources, right? The STORM project from Stanford.
Yes, STORM. That was detailed back in February 2024. It wasn't just answering questions. It was a whole system of agents designed to autonomously research a topic and write a complete structured Wikipedia page about it. Think about that, including citations, logical flow, section headings, all from a simple starting prompts like, "Tell me about the history of quantum computing." It was basically a proof of concept for automating deep, structured knowledge creation, like having a dedicated research team on demand.
That's incredible. But to automate something like that, the agents have to follow a clear process. To really get how they work, we need to understand the human blueprint they're trying to copy. How do we tackle complex questions where there isn't just one easy answer on Google?
Well, the sources make a key distinction. Simple factual questions, what they call desktop research. You might find a direct answer quickly. What's the capital of France? Easy. But complex questions speculating on legal outcomes, analyzing contradictory scientific papers, drafting a strategic business plan, these require a much more structured, multi-stage approach. It involves analysis, synthesis, dealing with ambiguity.
And there's a kind of standard human process for this, a blueprint that the agents are designed to replicate. What are the steps?
Yeah, there's a pretty clear 5-step blueprint that ensures rigor. It starts with goal definition. You have to be crystal clear on what you're trying to figure out. Second is plan creation. Breaking that big goal down into smaller, manageable steps. What information do I need first? Where do I look? Third, data collection. This is actually executing the plan, running the searches, reading the documents, querying the databases. Fourth is refining insights. This is crucial. It's the analysis part, looking at everything you gathered, identifying patterns, resolving contradictions, making sense of it all. And finally, step 5 is answer generation, taking all those refined insights and formulating the final, comprehensive, evidence-based response.
Okay, so that's the human model. Now, how do we translate that into a multi-agent workflow? This seems to be where the power of specialization really comes in, stopping one single AI from getting overwhelmed.
Exactly. You map those human steps onto specialized agents. The technical underpinning is that these agents need to be capable of reasoning logical thought, and they absolutely need access to tools, especially search tools, whether online or offline databases. So in a typical agentic research setup, you delegate roles very clearly. You might have Agent 1, whose only job is to take the user's initial, maybe vague request and clarify it into a precise overarching goal, the what. Then Agent 2 is the planner. It takes that well-defined goal and breaks it down into a logical sequence of research steps, the how. It's really important that the planner is separate from the goal setter.
Right, you want a dedicated thinker for the plan itself, separate from the one just defining the objective, and also separate from the one doing the legwork.
Precisely. Which brings us to Agent 3, the execution specialist. This agent's job is purely data gathering. It takes the plan from Agent 2 and uses its search tools to execute each step, retrieving the necessary information. It's focused only on collection. Then finally, you have Agent 4, and maybe even more agents depending on complexity. These are the synthesizers and answer generators. They get the original goal, the plan, and all the raw data collected by Agent 3. Their job is to do that, refining insights, analyze the data, check for inconsistencies, maybe identify gaps, and then construct the final, coherent, contextually rich answer grounded in the evidence collected.
Okay, this is the part that felt a bit underdeveloped in the initial script, but it sounds critical, this feedback loop. What happens if Agent 4, the synthesizer, looks at the data from Agent 3 and says, hang on, this doesn't make sense, or there's a huge piece missing here?
Ah, yes, that iterative nature is key to making this truly robust, just like real human research. A good agent system doesn't just plow ahead if the data is flawed. If Agent 4 detects a significant gap or a major contradiction, it doesn't just try to paper over it. Instead, it sends a structured message back, usually to the system's orchestrator, or maybe directly flagging it for Agent 2, the planner. This message would effectively say, analysis shows insufficient data on subtopic X. Please refine the plan to specifically target details of missing info. Agent 2, the planner, then gets this feedback, revises the research plan, maybe adds a step to search patent databases, or cross-reference with financial reports and gives the updated plan back to Agent 3 for another round of data collection. It builds knowledge step by step, refining as it goes. This ensures the final output isn't just fast, but also comprehensive and reliable, mirroring how thorough human research works.
The bigger picture here, the strategic implication, seems massive. It's really about augmenting human experts, not replacing them, right?
Absolutely. The goal is augmentation. By letting AI agents handle the time-draining research grunt work, the recherche beat, human professionals get their time back.
Time they can then spend on the things humans do best. High-level strategic thinking, creativity, innovation, making nuanced judgments based on the synthesized information.
Exactly. The human becomes a highly leveraged decision maker, amplified by these tireless, specialized research agents. It fundamentally changes the economics and speed of knowledge work.
Okay, so we've covered getting reliable connections with embedded tool calling and scaling up complex research with agentic research. Now let's have the third pillar, tackling the problem of precision, especially when dealing with large internal knowledge bases. This brings us to agentic RA optimization.
Right, retrieval augmented generation, RG. It's become the standard way to make LLMs knowledgeable about your specific company data, your documents, your databases. But classic RG runs into a big problem when the knowledge base gets large and messy, particularly when you have a single massive vector database containing information on wildly different topics, technical docs, billing info, HR policies, all jumbled together.
Yeah, the noise problem. You ask a simple, specific question, maybe about a technical issue. But the retrieval step pulls back chunks of text about billing and HR too, just because some keywords vaguely matched or they were nearby in the vector space.
Exactly. The retrieved context chunks are often imprecise, partially irrelevant, or just plain wrong. The LLM then has to try and generate an answer based on this noisy, confusing mix of information.
Which leads to weak answers, hallucinations, or the LLM just sounding confused. It's like asking a librarian for a physics book and getting handed cookbooks and tax guides along with it. The core signal is drowned out.
That's a perfect analogy. Agentic RA is designed to solve exactly that. Instead of one big, noisy retrieval step, it uses a multi-agent strategy to break the process down. It segments the query pipeline into specialized steps to ensure you only retrieve highly relevant information.
It's like having specialist librarians, one for physics, one for cooking, one for tax law. You go to the right specialist first.
Precisely. And the sources we looked at provide a really concrete technical setup for this. Implementations often use frameworks like Crew AI to manage the agents, maybe something like IBM's WatsonX.ai for the powerful LLM inference needed for generation, and a vector database like ChromaDB to store the knowledge. But there's a critical prerequisite here. This whole precision strategy relies on starting with separated data. The examples use distinct source files like counting.txt, billing.txt, technical.txt to create separate focused collections within ChromaDB from the outset.
So the intelligence isn't just in the agents. It starts with how you organize the data before the agents even see it. You don't expect the agents to magically sort a messy database. You give them clean, pre-sorted sections to work with.
The pre-siling is fundamental. It sets the stage for the agents to work effectively. Once you have that, you implement the core solution, the 3-agent pipeline. This is where the precision really happens. Let's break down Agent 1.
Okay, Agent 1, the first step in the chain.
Agent 1 is the query categorization agent. You could also call it the collection selector. Its job is very narrow, very specific. It takes the user's query like, my VPN connection keeps dropping, what should I check? And its only task is to assign that query to one predefined category. In our example, maybe those categories are technical, billing, or account. So for the VPN query, it should just output technical.
Seems simple, but you mentioned the importance of constraints here. How do you make sure it only outputs the category and doesn't, try to answer the question itself or give a wishy-washy response?
That's absolutely critical for the whole pipeline stability. You engineer this constraint in 2 ways. First, the prompt given to this agent is very strict. It tells the agent its only job is to categorize, not to answer, not to explain. Just pick one category from the allowed list. Second, and this is vital, you enforce the output format using a schema definition, often a pydantic model in Python implementations. This model forces the LLM's output into a specific JSON structure, say category, technical. Why JSON and pydantic? Because it guarantees the output is machine readable and contains only one of the allowed category words. If the LLM tried to output free text like, well, that sounds like a technical issue, the next agent wouldn't know what to do. The strict JSON schema prevents that ambiguity entirely.
Got it. That strict, validated output structure is the key to reliably passing information between agents. So once Agent 1 reliably outputs technical, what happens next with Agent 2?
Agent 2 is the context retrieval agent, the specialized retriever. Its behavior is entirely driven by that clean, structured output from Agent 1. It receives the category technical, in this case, as its main instruction. This agent has access to a specific tool. Let's call it the query collection tool. And here's the optimization magic. The tool uses the category word technical passed from Agent 1 to target its search only within the corresponding pre-siloed ChromaDB collection, the one built solely from technical.txt. So instead of searching the entire, potentially massive and mixed database, it searches only the small, highly relevant technical section. This dramatically narrows the search space.
Meaning the context it retrieves is almost guaranteed to be relevant to the original technical query because it completely ignored the billing and accounting documents.
Exactly. The noise is surgically removed before retrieval even happens. You get precise, relevant context chunks, and the retrieval itself is often faster too because the search space is so much smaller.
Okay, pure precision through that targeted retrieval.
Yeah.
So Agent 1 categorizes, Agent 2 retrieves highly relevant context from the right place. Now Agent 3 has to put it all together into an answer for the user.
Right. Agent 3 is the response generation agent, the generator. It gets brought into play with 3 key pieces of information. The original user query, my VPN keeps dropping, the category determined by Agent 1 technical, and most importantly, that highly precise, relevant context retrieved by Agent 2 from the technical collection. This agent uses a final tool, maybe generate response tool. The core action of this tool is to intelligently combine the user's query and the retrieved context into an optimized prompt template. These templates are usually carefully designed, often following best practices from the LLM provider like OpenAI or Anthropic or IBM, to instruct the LLM on how to prioritize the provided context when formulating its final answer. It tells the LLM, essentially, base your answer on this specific information.
And just like Agent 1, to make sure this final answer is usable by whatever system requested it, like a chatbot interface, Agent 3 probably also needs to output its response in a structured format, doesn't it?
Absolutely. You don't want just a raw text dump at the end. For reliable integration, Agent 3 also typically uses a pydantic model, maybe called final response, to structure its output. This ensures the final output is clean JSON, perhaps like category, technical, confidence score, 0.95 response. Based on our technical documentation, VPN drops can often be caused by outdated client software or specific firewall rules. Please check X and Y.
That structured output makes it super easy for the front-end application to display the category, maybe confidence level, and the actual natural language answer clearly to the user.
Precisely. So the end result of this three-agent pipeline is a RAG system that effectively sidesteps the noise problem plaguing traditional RAG. It accurately figures out the query's domain, pulls context only from the relevant knowledge silo, and then generates a reliable, contextually accurate answer based on that high-quality information.
It's really robustness and precision achieved through breaking the problem down. Specialization and delegation seem to be the common threads here.
It really is the unifying theme across all three areas we discussed, whether it's ensuring stability in real-time interactions using embedded tool calling,
Or scaling complex knowledge work efficiently with agentic research.
or achieving that pinpoint accuracy in database retrieval with Agentic RAG. The core principle is the power of specialization. Breaking down complex AI tasks into smaller, focused roles for different agents or different components like the embedded library consistently leads to better, more robust, and more reliable outcomes compared to relying on one giant do-everything LLM.
We're essentially engineering the process of intelligence itself, distributing the cognitive load.
That's a great way to put it. And what's exciting, as you mentioned, is how extensible this is. The sources hint at further optimizations, like using different types of LLMs for different agent roles.
Right, like maybe Agent 1, the categorizer, only needs a small, fast, cheap LLM because its job is simple pattern matching on keywords.
Exactly. But Agent 3, the final response generator that needs nuance and fluency, could use a much larger, more powerful, perhaps more expensive model. You optimize for cost and latency by using the right model for each specific task.
Which leads us nicely into our final provocative thought for you, the listener, building directly on this agentic RAG idea. We've seen how it masters internal knowledge. But think about this. What if we added a fourth agent to that RAG pipeline? An agent that comes after Agent 3 has synthesized the internal answer. This fourth agent's sole purpose, its specialized role, would be to evaluate the situation. Based on the query category, the internal answer's confidence, maybe even the phrasing of the original question, it would decide, is the internal answer sufficient? Or do we need to delegate this query out to the live internet for the absolute latest information?
Ooh, that adds a whole new dimension. A web delegation agent. That introduces some fascinating challenges, though.
Like what?
Well, that agent needs sophisticated reasoning. It's not just executing a tool, it's making a judgment call about knowledge sufficiency and timeliness. It needs to weigh the internal data's quality against the potential need for real-time info. Is the question time-sensitive, like what's the current price of Bitcoin, versus explain our company's billing cycle? What happens if the external web search contradicts the internal database? Which source does it trust? How does it handle the latency of a web search?
Exactly. That fourth agent becomes the bridge, the intelligent gateway between the company's curated internal knowledge and the dynamic, sometimes messy, live internet, all managed within this reliable, specialized agent framework.
That really would be a significant step towards creating truly comprehensive, context-aware AI assistants. It's a glimpse into the next frontier of agent capabilities.